Hey everybody, and thank you so much for tuning in. If you didn't catch the Chapter 0 video that I did to welcome to class, my name is Alex, and we were talking about sensation perception this semester. So the first chapter is exactly what you would expect. It is a chapter all about introducing the topic of sensation perception, and that is what we are tackling today. Just a quick kind of warning, I am trying to have these videos be about an hour and a half. So anywhere between 60 minutes and about 80 minutes. That's where I'm going to try to squeeze it in. Obviously, you could go on forever about this stuff, but I'm going to try to hit kind of the key ideas and some of the tricky elements and things that I think you should know whenever you are getting an education and in sensation perception. So let's get into it. Like I said, this is a chapter very much probably what you would predict from a early chapter, where we're going to be talking about defining our terms. What is sensation? What is perception? I want you to go ahead and start thinking about what the difference between those two might be, because that's a topic we're going to be covering or touching on throughout the semester. We're going to do a very quick history of sensation perception. And when I say quick history, I mean in like 15 minutes or so. I want to kind of keep it short because I know that a lot of you, whenever you leave this class, you'll probably never need to know the name Gustav Fechner again, or Ernst Weber. You probably won't need to know them by name, but it is important, I think, to know where those ideas came from and kind of what led to those transitions in psychology. But more about that later. We'll talk about psychophysics, which is kind of the study of objective reality and how it bumps up against our internal worlds. In other words, how we take something that is objective, like a physical stimulus, and turn it into a private internal perception, an experience. So we'll talk about the relationship of that, and then we'll talk about signal detection theory. And then if we have time, which we will, we'll talk a little bit about neuroscience broadly at the very end, kind of introducing those ideas about the brain, the neuron, and how we study, how we measure those things. So let's get into it. I got a bunch of videos for you here. I would say the most important ones, though, because I don't expect everybody to check out these videos necessarily, but I would say that the Plato's Cave can be really helpful, and we're going to talk about that a little bit. It's not covered in your book, which is why I wanted to include this link here for anybody who's feeling a little bit lost when we talk about that. And then I have the crash course opening video for sensation perception. Y'all are college students. You probably know Crash Course by now. Hopefully, you've been able to use it in the past for help. It's a great series of videos by the Greens. Is it run by them? I don't know. But John Green and Hank Green, they always kind of, we'll have like a crash course on history or whatever. The crash course on psychology, and in particularly in sensation perception, is helpful, and it's going to cover a lot of the early ideas here. So if you get to the end of this video and you're still a little bit confused, that can be a nice way to brush up on your knowledge and review what you learned. So let's get into it. I love starting this class out by asking and having us think about whether or not psychology is one of the sciences or one of the humanities. And now whenever I ask this question in a classroom, there will be kind of an awkward pause, and people will reflect on it. And then finally somebody will break the silence and they'll say, what exactly is a humanities? Which is a great question. I feel like it's kind of a term that may be less in vogue these days. But humanities would be like history, English, art history, or even art. What else? I'm kind of blanking on this. Communications, sometimes people will say that that's either one of the social sciences or one of the humanities. But you get the idea. Is it one of those, or is it more like biology and chemistry and physics, which we think of as like the hard sciences? And so while I'll let you think about that, I think that the answer is both. I think that psychology draws a lot out of the hard sciences, the quote-unquote hard sciences, like biology, chemistry, physics. We're going to be touching on all of those ideas this semester. But it also is concerned with what it means to be a human, what it is to experience the world, which is what the humanities is all about. When you talk about literature, when you talk about composition, or you talk about art, or history, those are, or anthropology, those are kind of diving into those questions. And I think psychology might be unique because it kind of does both. It is both very technical, but it is also something that we can study to help us understand ourselves and what we experience, but maybe more importantly, what other people experience day in and day out. So sensational perception is going to, like I mentioned in the previous video, be where the rubber hits the road. This is really kind of the dividing line between the external physical world and the internal experiential world. So what is a sensation? This is, I'm going to say it, this is a good question. And the reason why I think it's a good question, but maybe not, I don't think this is a good question for the exam, so I'm not trying to hint that this is going to be a question on the exam. But the reason why I think this is a good question is because I think on one hand it's very, very simple. You could say a sensation is anything you experience, right? You could leave it as boring and as simple as that. But once you start picking at those words, sensation is something you can experience. Okay, well, what do you mean by something? What could qualify as a something? Is an idea a sensation? I don't know. I don't really think that it is. And what do we mean by something that we experience? So what does experience mean, right? Well, that means that you kind of take it in. Well, do you mean like eat? Or do you mean, you see what I mean? Like when these kind of easy definitions are tricky because it really causes us to kind of think critically about what these individual words mean. And so the textbook gives this very simple, straightforward definition, that a sensation is the detection of an internal or external event. And so this could include an idea, right? Because an idea could be like an internal stimulus, right? But we're also talking about an external stimulus. So like light, for example. Light is an external stimulus and we can detect it. When we detect it, that is our sensation. Perception, on the other hand, is going to be turning that sensation into something that our brain can comprehend. So kind of the process in which you're taking light and seeing it. Oh, I'm already falling into the trap. What do we mean by seeing? Does that mean that seeing is a sensation and not a perception? So we have to be very careful about how we're kind of talking about these. I will put it this way, though, that generally speaking, 9 times out of 10, when people are talking about sensation, they're talking about stuff that occurs in terms of detection. That's really a good way of kind of thinking about sensation. Sensation is equal to detection. It's all about detecting something. Perception, I think that the key word here, at least to me, the way that I think about it, is this word, translation. That perception is all about translating what you have detected. So, if you see light, you translating that for your brain to understand that, oh, this is a bright light versus this is a dim light, or this is a bright light for this circumstance, right? Because oh man, I feel like I'm already getting into the weeds, but if I'm talking about like a bright light, somebody's got their high beams on at night when it's pitch black, that feels extremely bright, right? But what if you are in the middle of the day and somebody has their high beams on? It doesn't really feel as bright as it does, right? That is a difference in the translation of that stimulus. So that means that it's kind of a perceptual thing at that point. But as we are going to see this semester, those kind of boundaries really get murky and they can kind of overlap in a lot of different ways. One way that I try to simplify this is, generally speaking, that perception takes place in the brain. So when we're talking about light, for example, when light is entering our eye, that is sensation. But the moment that our eye turns that light into an action potential, into a cell, into a neuron firing, an electrical impulse, that's when it turns into perception. We call that process transduction. We'll talk about it all throughout the semester. All right, so sensation is kind of what takes place on the way to the brain. So that's your eyes, whatever you use to detect that stimulus, your skin, your nose when you're smelling things, your tongue when you're tasting things, your ear whenever you are hearing things, and more particularly your inner ear when you're hearing things. So all of those are going to be detection, and then our brain is what translates those signals. All right, so I got my eye on the clock here. Let's do a quick history of sensation and perception in 15 minutes or less. So, as some of you know, but maybe not, because our department doesn't require history and systems of psychology as a required course for your major, so you can get through your major without really knowing too much about the early history of psychology, which is okay. I'm the person who teaches that class, so I'm supposed to tell you that it's deeply important and that everybody should have it required, but I love that class. It's really interesting. One of the things that we talk about a lot in that class is that psychology is a baby science. It still is relatively new science. That if you look at biology, you look at chemistry, you look at physics, those sciences, they have roots way back, in early human history. Psychology is a little bit more complicated. That psychology really kind of came along with the industrial area, and before that, it was kind of like a mix of philosophy and religion and medical care. But a lot of the roots of psychology are built into philosophy, which is the study of knowledge, right? And so philosophy started asking questions like, well, what does it mean to live a good life? What does it mean to be a person in the world? What does it mean to experience something? How do I know that what I experience is different, or is it the same as what you experience? And if I see the color green now, does that would I perceive that as the same green 20 years from now, or would it be faded in some way? Philosophy was asking questions like that, and it wasn't really until the later half of the 19th century, so in the 1800s, that people started using the scientific method to try to test these kinds of questions. And that is where our story begins. So sensation and perception used to be the domain of philosophers. This name right here, René Descartes, he's a French nobleman, a very interesting history. From the 1600s, he came up with that very famous phrase that you've heard probably a million times by now, I think, therefore I am, which is one of those things that you hear all the time. At least I did growing up, and I never really thought about what it meant, and I had never taken a philosophy class, so I didn't really know what it meant. And basically what René Descartes is saying here is that if I can think, if I have this internal process where I can think, then I know that I exist somewhere. Maybe I'm an angel in heaven and I am remembering my life here on earth, or maybe I am a brain in a jar that is being stimulated with electrodes, or maybe I am just a part of someone's dream. But if I can think, then that means that some part of me exists in some capacity. And so René Descartes kind of developed this, I think, in his early life. Kind of his history of this stuff was like he kind of freaked himself out asking these kind of deep questions, and kind of used reason and logic to try to prove that he existed, and kind of worked his way out that way. And for those of you that are philosophy nerds or just want to know more about this stuff, David Hume, who is one of my favorite Scottish philosophers, or one of my favorite philosophers, he was Scottish. He kind of did the opposite, where kind of once he started asking critically about the assumptions and testing his assumptions about the known world, kind of came to the conclusion like, look, maybe I don't know anything. René Descartes started there, saying, hey, I don't think I know anything, and then kind of started here, I think therefore I am, and kind of built his way out like that. He believed that we have immaterial souls. In other words, he believed in dualism. So he believed that our spirits were immaterial. In other words, they cannot be outwardly measured with any kind of scientific means, because it's spiritual, right? That there's some kind of maybe supernatural or religious component to that. Most people these days, when they're writing about sensation and perception, do so kind of through what's called monism, which is so dualism is the belief that there is a physical world and a spiritual or non-material world. Monism is the idea that everything can be measured, everything can be reduced to something that can be measured, maybe with a microscope, maybe with a telescope, maybe with some kind of measurement that we have not invented yet. So whenever I say that, I don't mean that to say that all psychologists are atheists or whatever. What I mean to say, though, is that when we talk about who we are, when we talk about what we experience, psychologists believe that if we can study the brain, we can get to the bottom of this, and that we can understand that. That whenever we talk about who you are, when we talk about your consciousness, that is electrical activation and chemical activation throughout your brain that kind of causes you to behave the way that you do. That your personality is a complex combination of your brain and the chemistry in your brain, and your life events and your genetics and all this other stuff, but it can be measured. That it's not like we have ghosts in our heads or anything like that. So we can boil down our consciousness into brain activation that makes it measurable. We'll be talking about that at the end of the chapter when we talk about the different measurements of neuroscience. So that's I started with René Descartes because as one professor that I have, one professor that I had liked to say, it's a really corny joke. You can't put Descartes before the horse, or something like that, right? It's the play on the name, the cart versus Descartes. Anyways, thanks, Christopher Newland. I hope you're doing well. He is the one that said that joke, which I butchered just now. Anyways, let's rewind back a little bit and talk about some of the early Greeks. This is one of the things that this used to be covered in our textbook, is no longer covered, but I think that it's actually really important to kind of consider and to think about as we make our way through the semester. So I'm highlighting it here, which probably means that it'll be on the exam. If I think it's so important that I want to bring it up and it's not covered in the book, then it probably is something that I want to test you on. Just hint, hint, hint. But Plato, who was the kind of the student of Socrates, basically Plato kind of came up with this thought exercise, and it's a really famous thought exercise, and it's a way that we can kind of think about what it means to be human and what it means to experience the world. And he basically kind of compared it to this fable, this fairy tale, or a parable, or riddle, or however you want to think about it, this metaphor. He said that most of our life, we are like prisoners that are chained in a cave, and we're all next to each other, and we can't really move our heads. We can see a little bit out the corner of our eye, but we're mostly just looking forward. And when we're looking forward, there is a fire behind us, and so that fire behind us is casting a shadow out in front of us. So we can see light and we can see shadows, and as we are chained here looking forward, there are going to be people behind us that are walking between us and the fire, and so we see their shadows on the cave wall in front of us, but we can't actually turn around and see them, but we can see their shadows, and we can see that maybe they're carrying objects. It looks like, based on this shadow, that maybe that somebody is carrying a big Grecian urn, and somebody else is carrying what looks like a manger, and somebody else is carrying something that looks like water. And basically the idea is that if you're looking at those shadows, you can probably reason what you're actually seeing, what's actually behind you. But because you're chained in this cave, you can't actually turn to verify that yourself. And so when we see those shadows, that's as close to reality as we can perceive, according to Plato. So, and if you want to extend this metaphor, basically he did, and kind of talked about how, like, if you educate yourself, you can break free of the chains here, and you can climb up out of that cave, and you'll see the world in all of its splendor and all of its magic and all of its color, and then you go down to free the other prisoners, and you tell them all these things that you saw, but they don't believe you because it seems too outlandish, and then they label you a poet and whatever, and an artist, and I don't know, some other nonsense that does, I don't know, he kind of goes off the rails with the metaphor there to try to explain what it's like to be a poet and what it's like to be learned. But I think really the more kind of interesting thing here is this notion that, according to Plato, that most of what we are doing is not actually directly experiencing the outside world. And if you think about this, there is some truth to that, right? Because your brain is not actually tasting things. Your brain isn't actually smelling things. Your brain is not actually having light put on it, right? What you are seeing is your eyes, and so that light is entering your eye, and your eye is going to turn that into some kind of electrochemical signal that is then going to go to your brain, and your brain is going to try to interpret it that way. So according to Plato, he didn't have an MRI machine or whatever. He wasn't scanning brains back then, but this metaphor is actually really helpful to try to understand how we perceive the world, that we don't experience it directly, that we don't experience the objective world directly, but we experience essentially like a shadow of it, kind of an indirect version of that reality. Here's kind of a diagram of what Plato's talking about, and you can see that this is where you would retreat out of there and all this other stuff. If this sounds familiar, there is a very popular movie series based on this idea. Sorry, I tried to time my coffee sips to be strategic, to let you think about what it might be. And that is The Matrix. If you haven't seen The Matrix from 1999, I know it's before a lot of your time, but I'm telling you, it holds up. The special effects look great. The story is super interesting, and it's a lot of fun. There's a lot of cool kung fu in it. And you've probably, I don't know, it's one of those things, it's like Star Wars, where like, even if you haven't seen this movie, you've probably gotten a lot of the ideas through cultural osmosis. But this idea in The Matrix is that a lot of people day to day are not actually experiencing the world. They're just kind of like in this deep sleep, and kind of their brains are kind of like being informed of what they are seeing. So what we see is not actually reality. It's kind of like a program, a computer program that we're all living in. All right. So that's enough history in pretty much 15 minutes right on the dot. Or actually, it was a little bit faster than that, so good job, me. All right, so psychophysics, and also let me hesitate for a second. We just talked about Plato. We just talked about Descartes, but we could talk about so many other people. I just don't think that it would be super helpful for a class like this to really get into weeds on that. But if you are interested in reading more about this kind of stuff, please let me know, because I would love to talk to you and give you some recommendations on kind of early thought exercises in psychology and philosophy. So let's talk about psychophysics. As I mentioned earlier, psychophysics is the science of kind of the interaction between the objective world and the subjective world. So it's like looking at the connection between physical events and psychological events. So whenever I touch something, and I interpret what I'm touching, what is that relationship? The relationship between sensation, and perception is essentially what we're talking about here. So psychophysics, it sounds very scary, right? Because it's got physics in the title there. But psychophysics is really kind of the early version of psychology. That a lot of psychology's history and its origin starts here, with people trying to measure our perception, and people trying to measure how we interface with light, and how we interface with sound, and how we interface with taste and smell and touch. So there are a few different measurement styles that we're going to be talking about this semester. I'm not going to go into too much detail here because the book does a decent job. I don't think this is one of those abstract things, but this is just one of those things where you can kind of keep it in the back of your head as we're moving forward, how we are able to measure the thresholds and our sensitivity to different kinds of sights, sounds, and tastes. Because as you know, it's not the same for everybody. That some of us are more sensitive to different kinds of stimuli than others. Some of us are extremely sensitive to specific kinds of sounds. So how are we able to measure that? That gets to the heart of psychophysics, because what we're doing is we are going to measure the external world to see what kind of impact it has on our perception. So absolute thresholds, for example. An absolute threshold is your ability to detect some kind of event 50% or more of the time. So for example, and you might get this at a driver's exam, where you are hearing these little beeps and you have to say whether or not you can hear it. It's been a long time since I've done a driver's test like that, so I don't know if it's different for those of you kids out there that just got your learner's permit. But those kinds of tests, they're kind of looking for your absolute threshold. They're looking for what the lowest decibel, what the lowest volume is of that sound for you to be able to detect it at least half the time or more. That is your absolute threshold. And we can look at absolute thresholds for our different perceptions, and they are going to be different from individual to individual. The 2-point threshold. The 2-point threshold is the minimum distance at which two stimuli can be distinguished as being separate. And generally speaking, we're going to be using these a lot when we talk about touch. I should have brought this in. I should have brought in some tweezers into my office to kind of give you an idea. But a 2-point threshold is usually done with skin calipers, where you have like these 2 points right here and you press on your skin. And if you try this with a pen, you can try it on your body right now. And I can feel that is 2 points. So those are 2 points against my skin. If I make them a little bit closer, if I make those points a little bit closer to one another physically, then now it just feels like 1 point. And so what we could say is that this is beyond my 2-point threshold because I can feel it as 2 points, and this is within my 2-point threshold because it feels like 1 point on my skin. So go ahead and give that a try if you want to. What you'll see is that not only is that 2-point threshold different from person to person, it is also different across your body. So if this is too close so that you perceive it as one thing on the surface of your arm, if you try it on your lip, you can easily tell that it is 2 separate points. And what that tells us is that our lip is way more sensitive to touch than our arm. And you can try to test the various areas of your body to measure that 2-point threshold. These are kind of some fun examples. You do not need to know this on the exam. These are absolute thresholds for our various perceptions, our various sensations, senses. I don't know how much time it took to calculate these, but you'll see that some of them are extremely specific. So our absolute threshold, the quote-unquote common threshold, so across most individuals, and in fact throughout the semester we're going to be doing a lot of broad generalizations, because what we're doing is we're looking at sensation perception as it is for most folks. Everybody is different from person to person, and so this may be true for you, it may not be true for you, and that's okay because we are all different. This is what's just for most folks. So the absolute threshold for vision for most folks is that you can see a candle flame 30 miles away on a dark, clear night. And if you don't have an idea of what that's like, imagine sitting in your dorm at Westfield and being able to see a candle light over in Springfield. That is ridiculous, right? That is really interesting. I would not have thought that my eyes were that sensitive to be able to pick out that more than half the time. For hearing, it's being able to hear a ticking watch 20 feet away in a very quiet room. For touch, it is the feeling of the wing of a fly falling on your cheek from 3 inches away. So I don't know what that was like testing that. Did they just have like a bunch of participants come in and they were just dropping fly wings on people's cheeks? And it's like, okay, we dropped it from 4 feet and they couldn't feel it. We dropped it from 1 foot and they couldn't feel it. From 6 inches they couldn't feel it. But at 3 inches they can. For smell, that is a drop of perfume 3 rooms away. For taste, that is detecting a teaspoon of sugar in 2 gallons of water, which is, to me, again, pretty shocking. Think about 2 gallons of water. And if you think about taking a teaspoon of sugar and pouring it in 2 gallons of water and taking another 2 gallons of water and not pouring that you would be able to taste the difference between that. That's what that is telling us. And then finally, the vestibular system, this would be that you can detect less than half a minute on a clock face. So if you think about the minutes, you take a clock face and it's divided into 60, that you can detect the rotational difference of half a minute. So very slight rotation. Just noticeable differences are the final kind of threshold, and these are when we are comparing two stimuli. So we are taking two stimuli and we are looking at the minimum change required in order for you to be able to detect that there is a difference. And yes, this is very similar to the 2-point threshold we were talking about with the surface of your skin, but this is like if I were to play one tone and then play a second tone at a slightly different volume. Maybe I turn it down just a little bit and then ask you, were those the same volume or were they different? If it was just barely enough that you couldn't tell the difference, then we would say that difference falls inside the just noticeable differences. So you can't really detect it. But if I go from really quiet to really loud, then that would be an example of it falling outside your just noticeable difference. So you can detect a difference there. And this brings us to Ernst Weber. Ernst Weber, German bloke who did a lot of research, has some really great mutton chops, but he, doing research on the connection between the physical world and the way that those physical events and stimuli impact us and whether or not we perceive them, testing absolute differences and things like that, what he found is that the relationship between a stimulus and our ability to detect it is a constant fraction. So, large stimuli are going to lead to large just noticeable differences, and small stimuli have small just noticeable differences. This is going to become something that we call Fechner's law, and I'm actually going to skip to that and then walk you through an example. So Fechner's law is this equation that kind of maps out the relationship between the external world and how it impacts what we experience. And you can calculate it like this. S equals K log R. Don't worry, you don't have to do any math in this class. I'm not going to make you calculate this or compute this, but I do think that it is important to kind of unpack what this equation is, and then we're going to rewind and look at an example of this in action. So S, what we are solving for, is going to be our perception. So this is kind of our internal understanding, our experience of that stimulation. R is going to be the stimulus intensity. So this can be measured physically. In other words, what I mean by that is that I can probably take a device and measure how loud something is. On your phone, you can measure in decibels how loud something is. There are different apps you can use, so you can use your camera to determine how bright something is. You can measure that in lumens, or how heavy something is. The key here is that it's physical, that it is external, that it is something that is empirical. And what I mean by empirical means that it obeys empiricism. So that means that if I measure it and that you measure it, that we will get the same thing, that we can agree on our measurements here. So there is no guesswork, there is no interpretation. It's simply, this is the physical intensity of it. That is R. And then K is going to be that Weber fraction. That is the constant proportion that Ernst Weber discovered between stimuli and their sensation. And that really depends on the modality of what you are measuring. So the Weber fraction is going to be different for vision, for hearing, for taste, for touch, and for smell. Okay, so what are we doing here? We're essentially, we are able to measure how big or how small our perception is if we know how intense that stimulus is and what the Weber fraction is. So let me rewind, because right now we're very abstract. Let me rewind and give you an example, and then I think this will start to make a little bit more sense. So let's say you pick up a bag of sand, and that bag of sand weighs 10 pounds. Not super heavy, but heavy enough that you notice that you're carrying something, right? So it's 10 pounds. Someone walks up to you and they say, hey, could you hold my bag of sand? So they give you this bag of sand, and so now they give you another 10 pounds. The question here is, do you feel a difference? Yes, absolutely you will. Even if you are the world's strongest person, you're still gonna feel the difference between 10 pounds and 20 pounds, right? It's double the it's double the weight. You're going to feel a difference. But what if you are carrying, the first bag that you picked up was actually 1,000 pounds instead of just 10 pounds? If you're carrying something that is 1,000 pounds and somebody adds 10 pounds to it, would you detect the difference then? That one's kind of harder, right? Like, I mean, I've never been able to pick up 1,000 pounds, but I don't think that I would detect the difference there, right? If I have 1,000 and somebody throws 10 more on top of that, that 10 by comparison is going to be so light that I'm probably not going to detect a difference there. And that is Fechner's law. That is essentially what Fechner is trying to illustrate here. So here is the relationship of S and R. So the physical stimulus intensity versus our perception of what we are experiencing. And so what we see here, and so you can imagine that just down here on the x-axis, I'm going to use volume. No, actually, let me use weight here because we just did a weight example. So this down here is going to be how heavy something is. And so let's say that this is 1 pound, 2 pound, this would be 4 pounds, this would be 8 pounds, this would be 16 pounds. You can see that it's just doubling essentially. I think this one is actually probably more like 64 pounds maybe. Yeah. So we have this on our x-axis, how heavy something is. And we can trace up here on this black curve to see where how strong our perception is. So for example, and here what we're saying that this is really high, or let me change this to really heavy. So this is really heavy stuff, and this is really light stuff. These being kind of our interpretation of that weight. This is our perception. This is how we have translated these physical intensities. All right, so when we're talking about 1 pound of sand, it's pretty light. When we're talking about 2 pounds of sand, it's also pretty light, but that's a pretty big difference in our perception. That basically the perceptual power has doubled from 1 to 2. And that's probably not all that surprising, right? Because we're talking about from 1 pound to 2 pound. It is double the physical intensity, but watch what happens when we double it again. So when we go from 2 to 4, you would expect that maybe the perceptual power would double again, but that's not what happens. You can see that it only really goes up about the same amount as it did from 1 to 2. In other words, when we go from 2 to 4, that increase in what we perceive is only about as much a difference between 1 and 2. And let's go one more. So going from let's do from 8 to 16. So when we are carrying something that's 8 pounds, we can see that we find that to be moderately heavy, right? All things considered, it's pretty high up on our axis right here. And then if we're trying 16 pounds is double, right? But what we're seeing here is that it's not actually twice as powerful. And in fact, it's actually kind of really only the same difference as the difference between 1 and 2, or the difference between 2 and 4, the difference between 8 and 16 is what we have. So what do we make of this? Basically what this tells us is that the more intense a stimulus, and this is a huge point, so if you haven't taken a lot of notes yet, this is one of the take-home messages of this whole chapter, of this whole class maybe, is that the greater the physical stimulus is, the more intense that physical intensity is, the harder it is to detect additional measurements. So if I'm carrying something that is 1,000 pounds, I probably am not going to detect another 10 pounds. But if I'm starting small, if I'm starting with 20 pounds and somebody throws 10 on, I can definitely tell the difference between that. If I'm carrying 1,000,000 pounds, there's no way I'm going to detect somebody throwing on 10 extra pounds. Probably not even 100 extra pounds at that point, right? But if I'm starting at 20 pounds and someone throws on 10, I can detect that difference, right? And if you don't believe me, you can try this yourself. You can try getting a couple of books. So for me, I got some books right here. I got my this first book, I got the second book, and I can notice a pretty big change. I'm putting a third book here, and that third book doesn't feel like as big a change as 1 to 2 did. 2 to 3 doesn't feel like as big a weight difference or as noticeable as a weight difference as 1 to 2. All right, so that is Fechner's law in a nutshell. If you're still a little bit unclear here, there's a great example in the slide notes here of a guy who's testing this out with sound, and he does this with his car stereo. Highly recommend it if you are reviewing this or if you want another example in a different modality. Okay, let's talk about how we measure these things. And again, this is one of those things that's kind of definition based, so I'm going to kind of speed through some of this stuff. The method of constant stimuli, this is if you're going to be presenting this in a random order. So you're going to be presenting, so this says stimulus level. You can imagine this as decibels. So we're detecting how loud something is. And so maybe we're going to play some soft, some loud, but the key is that we're kind of not really in any kind of order. We're just going to kind of play it, sometimes soft, sometimes loud, sometimes in the middle, and by doing it at one at a time, that helps us find our absolute threshold of, okay, I hear it versus I don't hear it. All right, the method of limits, this is where we are going to present it in order. So we're going to be starting out, and again, if we're using volume here, where we're going to start really soft and slowly have the volume raised until we can hear it, or we can work in the opposite direction where we start really loud and then go until we can't hear it anymore. And so it's presented in order here, and then we tell the experimenter or the doctor, yes, I can hear it now, or no, I can't, I no longer hear it. This is very similar to the Yanni versus Laurel tool that we used in Chapter 0, if you remember that. And then we have the method of adjustment. The method of adjustment is where you were able to physically move the slider or the knob to a point where you can hear it. And so that way you're able to actually control what you're hearing or what you are perceiving. So if you if your doctor said, hey, turn this up until you can hear it, that's an example of method of adjustment. If I gave you some coffee and I said, hey, put enough Splenda in here until you can taste it, that's also the method of adjustment. You're adding or you're subtracting until you pinpoint your own threshold. All right. You like that animation? How cool was that? So which method is best? Really, it depends on a lot of different factors. It depends on which of these factors are most important to you. So for example, the method of constant stimuli, which is random, that is going to help you avoid any kind of expectation effects. The example that I gave of starting really soft and kind of getting louder, if you're doing that, or if you're going the opposite direction, starting loud and going soft, you might have an expectation where you think you hear it, but maybe that's just kind of your memory of it. Maybe your ears are ringing. And so the method of constant stimuli, because it's random, avoids expectation. The method of constant stimuli, that can be good, having it random, but it can require a lot of trials. So even though it does avoid expectation, it means that you have to spend a lot of time doing it. The method of limits is okay, but it's not quite as good at getting the absolute threshold because it has that kind of expectation effect. And so when people do this, they usually use the staircase method. We'll look more at that at one of the research articles that we read this semester. But the idea of the staircase procedure is that you're going to start soft with like kind of a really low intensity stimulus, and then you're going to get more intense until, well, actually, hold on. Yeah, if we're starting small, we're going to move until they could detect it. And then once they detect it, we're going to go back down a little bit. And then if they don't detect them, we're going to go back up. Basically trying to, move in order up and down until we pinpoint exactly where that threshold is. And the method of adjustment is really, really fast and it's efficient like that, but it's the least accurate of these three. When we compare experiences, though, this can be a little bit tricky because if I'm trying to measure my threshold for sight, that doesn't always really translate to my perception of sound or my perception of touch. And so people will use psychophysics to try to understand how these modalities compare to one another, which is going to lead us to one of my favorite images or my favorite figures in just a second here. That basically what you're looking at here are Weber fractions for shock, for length, which is visual length, I should say, for sweetness and for brightness. So across the different stimuli, you can see that the fractions vary differently. But whenever, and don't worry, this is just illustrative. Like, you don't have to commit that to memory what those different fractions are. But this is going to come in handy when we try to account for how things compare across each other. So this is one of my favorite figures because these researchers were trying to compare different modalities. How intense is something that you touch, and how does that compare to something that you see? And so the way they do this is they basically are going to use the same thresholds and methods that we just talked about to try to make these comparisons across different sensations. So, for example, let's say I'm going to start here in the middle. So we got the smell of bacon frying is slightly more intense than the pain of a mild headache. And the smell of bacon frying is slightly less intense than the brightness of low beam headlights at night. But they're all pretty close, right? But if we look at the coldness of snow, and those of you that are, well, most of you are New Englanders, you're very well aware of how cold snow is. The coldness of snow is less intense than the smell of a skunk. And the smell of a skunk is slightly less intense than the brightness of high beam headlights. So you get the idea. That basically people use these thresholds to try to compare across each other. The reason why I think this is just fascinating because it tells us, staring into the sun is is more intense than the heat of scalding water. And that both of those are more intense than the sound of a fire engine. You can test that yourself if you want to. Now, Gustav Fechner, that guy that we were talking about with Fechner's curve and Fechner's law, he almost lost his sight because he stared into the sun so much, which is kind of, I don't know, to me it's kind of funny because we're told over and over and over not to stare into the sun. But he's a scientist. What does he know? He's just testing this out himself and almost lost his vision because of it. And if you're curious about what this super taster, medium taster, and non-taster is, we're going to revisit this in the final chapter of the semester. But basically what this is showing is that depending on your genetics, some people might experience a taste way up here to be worse than the brightness of the sun. But other people, based on their genetics, are going to perceive that as a little bit worse than, more intense than the smell of frying bacon, and others are going to barely perceive it at all. We'll talk more about that, but I wanted to call your attention to that because if one of the things that we talk about isn't true for you, that's okay, because this is just broad trends that we're talking about here. All right, so there's Fechner's law. I'm going to pause it for a quick second because I need to take a quick break because my mouth is running dry. We'll finish this up by talking about signal detection theory and what's going on in the brain when we are perceiving things. All right, okay, so I'm back. All right, we're talking about signal detection theory. I was going to say thank you for your patience, but you weren't there where I just had 3 minutes to just kind of unwind and just kind of like relax and drink coffee. So let's talk about signal detection theory. Now, signal detection theory is kind of tricky to talk about. You may talk about it in some of your other classes, though. Sometimes it comes up in theories of personality. Sometimes it might come up in stats. Sometimes it really comes up a lot when we talk about assessment. So when we're talking about like assessment or diagnosis, things like that, you can learn about signal detection theory. But it comes up a lot in sensation perception specifically. And the reason why is because it is a way of approaching your data, of approaching results, of approaching how we conceptualize data. And most times when we think about like if you get a test or an inventory, a personality scale, a lot of times when we're just analyzing it, we might just add up all the values, or we might get the average or whatever, the mean, the median, the mode. And what signal detection theory does is it's a different way of looking at it. You can look at it like that if you want to, but signal detection, like looking at means and cumulative effects and sums. But we can also look at how sensitive certain measures or inventories are. And so signal detection theory is going to tell us about bias, tell us about likelihoods. And as you'll see in a moment, because I'll give you a really vivid example with Where's Waldo. But basically, instead of thinking about behavior as an average or as a mean, we can think about behavior as a false alarm or a correct rejection. You'll see what I mean. Let's try this out first by playing Where's Waldo. If you haven't played Where's Waldo before, I'm so sorry that your childhood was like that. But I remember, like, this could be like a millennial thing or whatever. But like as a kid, Where's Waldo? Like you know how like they say like in prison, you know, like cigarettes are like currency or whatever. In my kindergarten, Where's Waldo books was like currency. And specifically a Waldo book where somebody didn't circle something in or scribble in it and ruin the game. If you're not familiar with it, basically you're going to get a really vivid image and you have to try to find this guy called Waldo who is wearing white and red. And if you're playing for the first time, this is kind of what you would expect, where you see a lot of white and a lot of red, and so it makes it really frustrating because oh, there's Waldo. Nope, that's not Waldo. That's just a hat that is white and red. Oh, there's Waldo. Nope, it's just a kilt that is, or an apron that is white and red. And that's always the gimmick with these. So scan through this image and let me know if you find Waldo. I tried to make this one easy. I tried to make him right here. Whoops. Tried to make him right here, dead center of this. Usually, we talk about this in cognitive psychology, whenever people are studying an image, they either start in the left and then scan forward as if they are reading, or they sometimes will start in the center and then spiral outwards looking. But so that's why I try to make this easy by putting him pretty much in the center, but there we are, we see him right there. If you didn't see him, then we would call that a miss, M-I-S-S. And we'll redefine these terms in a second. But he was here, and so we saw him. If you did see him, we're going to say that was a hit. The stimulus was there, and you did detect it. So let's check out this one. All right, so take some time. Let me know if you see where Waldo is. All right, so Waldo is not in this one, right? So Waldo isn't in this picture. If you looked at this picture and you said, wait a second, there he is, there's Waldo, that's him, then that would be an example of what's called a false alarm. So you thought you perceived it when in fact it wasn't actually there, or you thought you detected it, but it wasn't the stimulus you were hoping for. If you looked at this and you said, nope, I did not see him, then that's what we're going to call a correct rejection. And I know that this is hard to read, because I'm writing with red on an image that has a lot of red, but that's okay. Like I said, I'll define these terms again later after this. All right, what about, where'd it go? Oh no, where's my other Waldos? Oh well, if you have the slides on Play-Doh, then you'll see the other Waldos. You can play along and test your own self. I think that maybe PowerPoint kind of removed some of these because the PowerPoint was too big to upload to Play-Doh. All right, so in doing this Waldo exercise, there are 4 different responses that we can have. We can break these down into hits, which is where you detected a stimulus and it was in fact there. That is a hit. It would be a miss if Waldo was present and you said he wasn't there. In that case, you reported that a stimulus was gone, was absent, but it was there. A correct rejection is where you reported that a stimulus wasn't there and you were correct that it wasn't actually there. And then a false alarm, which is where you say that it was not there when in fact it was. So those are the 4 different kind of responses. And this can tell us about an individual's bias. And usually when we talk about bias, at least I feel like in the media and in the culture on social media these days, when we talk about bias, it's almost always like a political thing or, or whatever. And I don't mean it like that at all. I mean bias in its more kind of simple, basic definition. Are you more likely or less likely to respond a certain way? So here, let's say if you have a tendency to say, yes, I see Waldo. There he is. There he is. Nope. There he is. Nope. There he is. Nope. There he is. Nope. Then that is, you are very sensitive to Waldo. That you are saying that he's there. There's a lot of false alarms and a lot of hits, but a lot of, you have a lot of false alarms and not that many misses, and not that many correct rejections either. But if I look through this, and let me go back to this previous example. Oh, weird! I don't know what's going on with my PowerPoint, but it's not even showing me the old Waldo now. But if I looked at that Waldo and I said, I'm not so sure that that's Waldo. It looks like him, but it might not be him. I'm going to keep looking. Then that would be an example of you being biased, but in the opposite direction, where now you're being too careful, you're being too conservative about what you are defining as Waldo. And this is going to cause you to make mistakes. It's going to cause you to make some misses, where Waldo was present, but you said that he wasn't. But it's also going to result in you having a lot of correct rejections, where you now look at this guy up here in the top right-hand corner, and you say, nope, that's not Waldo. Whereas somebody who is more eager and is more Waldo happy is going to be likely to say that something that looks kind of like Waldo is in fact Waldo. Another example here, and again, I'm bummed that that this image isn't showing over here. I had an image of a mammogram over here on the right-hand side, because this is something that is used a lot in different, or its importance can be used in a lot of different fields, like in healthcare. If we're looking at a mammogram, and we talk about this in my cognitive psychology class too, actually, that if you're looking at a mammogram, it's really, really helpful to notice, like, yes, that looks like cancer, but that doesn't look like cancer. That looks a little bit like cancer, but I know that it's not because I've seen this before, but that does look like cancer. That being able to diagnose specific kinds of tumors or masses is extremely helpful, and being able to know when something is there versus not there can be critically important. And as we're going to see in just a little bit, how it has bearings on the criminal justice system as well. This example that I have here for you, I'm not going to play it on this video because it would be very, very annoying, but what I have here is a bunch of white noise, so you hear kind of some static, and then a piano. And one of the things that I like to do when I'm doing this in class is I will have the static going, and I will hit a piano key and then ask people, did you hear the piano above the noise? That's also an example of signal detection theory. And this breaks things down into signal versus noise. You may have heard that phrase before, of the signal versus noise. I want to make sure that it's clear, though, that noise does not necessarily mean auditory. It doesn't necessarily mean actual noise, actual static, actual things that you hear. Noise is really just anything that is not the signal. The signal is what you're trying to detect. Everything else is going to be noise. So if I'm trying to find Waldo, for example, if I come back to these examples, I don't know what's going on here with PowerPoint. It's too bad. But if I'm looking at that, everything that's not Waldo is going to be considered signal. Everything that's not Waldo is considered noise, but Waldo is the signal. If I'm thinking about trying to detect that piano is now the signal, and the static is the noise. If I am sipping some coffee and I'm not sure if there's cream in here, and I am trying to taste it, everything that's Splenda is noise. The coffee is noise. You're trying to detect the cream in there. The cream would be the signal. So a signal really depends on what it is that you're measuring. So in the previous example, that signal is Waldo, but it's really just anything that you're trying to detect. And the noise is going to be anything that is irrelevant that might distract you from that. So the book gives the example of a shower and a phone call. This is one of those things that if especially like if you are expecting an important call, is very relevant, where like you're in the shower and you think you hear your phone ringing or you think you hear it buzzing, and then you check it and it was a false alarm. It wasn't actually buzzing or vibrating. But that threshold at which you decide, yes, I think I heard it buzzing, versus no, I didn't hear it buzzing, that can change day to day. It can change on how awake you are. It can change on how late in the shower it is, how late in the day it is. It can also change on if you are expecting a phone call or if you are not expecting a phone call. So this tells us about the biases that we have in our detection. So that point at which we decide, yes, that's Waldo, or yes, that is my phone buzzing, that is what we call your criterion. So that is going to be your internal threshold at which you decide, I think that I detected something. That is your criterion. And your criterion is not fixed. It can change across the day. It can change based on how tired you are or how awake you are, or whether or not you're being rewarded or punished for those things. So for example, if I gave you the Where's Waldo and I said, the first person to find Waldo, I'll give them $1,000. That's going to make it, and it doesn't matter if you get it wrong, that's going to give, a lot of people are going to send me the first thing that they see, because now I've incentivized them to try to find that signal, and their criterion is going to be much more relaxed than it would be if I said, here's Where's Waldo. If you get the wrong answer, you owe me $1,000, right? Now you're going to be really, really careful, and you're not going to act on Waldo unless you're absolutely sure that it is Waldo. Sensitivity is going to be how easily you can detect the difference between signal and noise. So sensitivity is how much does the signal stand out from its surroundings. So for Waldo, if Waldo was red and white and everything else was blue, he'd stand out pretty easily, right? So his sensitivity would be much higher. If we're talking about a phone, to go back to this example, if I turn the ringer up, that would be turning up my phone's sensitivity. Now it stands out more from the noise. We call that a measurement of D prime. D prime is sensitivity. It's the relationship between hits and false alarms. How easily you can detect the difference between a hit and a false alarm. That is your sensitivity. All right. Oh man, this is too bad that, hold on, let me see if I can fix this, because it would be really a shame if, it's saying it can't be displayed, but you can, I don't know if you can see it over here. Nope, it's already gone. So weird, I don't know what that's all about. But the figure that I have in your notes is, you'll see the Where's Waldo tableau, and you'll see that it can be hard to find Waldo, but if you turn everything around him to be black and white, Waldo stands out immediately. And so what we've done in that case is that we have increased Waldo's sensitivity. Now he sticks out because he's the only thing that's colored in the environment around him. The way that we graph these results out is called a receiver operating characteristic curve, or an ROC curve. An ROC curve is a graphical representation of your data using signal detection theory. And so that would be like, let me see if this image, okay, hold on, I'm gonna pause it and see if I can figure this out, because I really wanna show you this. Okay, sorry about that, I'm back. I realized what it was. I was telling you that that the file was almost too big. What happens is, as I was drawing stuff on this, it was basically deleting the future images to save the writing here. So here, this is an example of signal detection where you would say like, this is cancer, but that this is not. It looks like it might be, but anything that would not be the signal that you're looking for would be considered noise here. Here is the example with Waldo that I was referring to. So now Waldo stands out, right? He stands out very vividly because we have increased his sensitivity. We've increased the discrepancy between the signal and the noise here. Here is the ROC curve that I was trying to show you. So basically, the closer this curve gets to this top left-hand corner, the more sensitive the stimulus is. The closer it is to this straight line, the straight diagonal line, the closer it is to chance. The closer it is that your participants are just guessing, or your clients are just guessing about what they experience. If it's lower than this, if you find your curve is down here in the bottom right, that means that they're actually getting it wrong more than they're getting it right. So generally speaking, something that is extremely sensitive is going to be hovering up over here, because if you look at these axes, that means that we have a very high hit rate but a very low false alarm rate, which is a good thing, right? But if we have a very high false alarm rate and a very high miss rate, which is what you're looking at here, from this is a low miss versus high misses, then this would be really, really bad accuracy. You're getting it wrong more than not. If you're just guessing, then that's what we have right here, which is half the time you get the hits right, half the time you get the correct rejections, half the time you get the false alarms, and half the time you get the misses. So that's how to interpret these ROC curves. You'll see them out in the wild every now and again. All right, so to show you an example of this in the real world, remember this man. All right, so tell me, in just a moment, I'm going to show you a different array of images, and I want you to tell me if you saw that individual or not. One example, and I wanted to use this example because I know a lot of you are criminal justice majors, and you're just taking this because you're getting your psych minor or whatever, and at this point in the class you're like, oh my god, what have I signed up for? This has no bearing at all on criminal justice. It does, actually. And when we start talking about vision and hearing, you'll see that there's a lot of connections to be made with criminal justice, but I'm going to give you an example of this out in the real world. That can pertain to social policy and things like that. So the example is police lineups. There's a lot of research out there that looks at police lineups and how effective they are, and whether or not they're useful or not useful. How useful are they at catching a perp and things like that. I don't know if perp is the correct terminology here. That's just what I saw on Law and Order. So a police lineup would be, you've seen it before on TV and movies, where you have a bunch of people line up and then you have somebody come in and they say, yes, that's the man, that's the dude. And so the issue with police lineups is that not oftentimes, but we know in the past that people have been falsely accused using police lineups, which nobody wants, right? Everybody wants to reduce the amount of people that are falsely accused here. So we have to now think about, is this police lineup style best for what we want? If we want to try to reduce the amount of falsely accused people. And if you're thinking about signal detection terminology, what we're looking for there is false alarms, right? So the question is, what is the best way to identify a perpetrator while you are trying to keep false alarms as low as possible? So maybe it's a simultaneous lineup, like you see here, where you see 6 individuals and you have to say, yes, that is the guy. You're pointing at the person. So this is a simultaneous police lineup style. But it's not the only kind of police lineup style. Some people have experimented with sequential lineups, where instead of having all 6 people present at once, maybe we give this individual a set of images, and they have to say whether or not it was the one that they saw. So here we're looking at perp number 1, perp number 2, perp number 3, number 4, number 5, and number 6. And in this case, the individual, the witness, is saying, yes, that's the person, as they go through it. So which one was the man that we saw? We actually saw person number 3. You probably got that. You probably got that right if I had to bet. But was it easy because it was simultaneous, or would it have been easier if it were sequential? Would you have made errors if you had done sequential? So in this case, what we find is that with the sequential method, that ensures about 80% accuracy on that particular experiment. which is really, really interesting because the traditional simultaneous lineup only gives us about 60% accuracy. So we might, if we're just looking at accuracy, say, okay, well, I guess that means that the sequential method is best, and that's what we should use. But if we look at signal detection theory and we break this out in terms of hits, misses, false alarms, and correct rejections, now what we see is that the sequential method actually has a false alarm rate of about 60%. In other words, more than half the time, someone is mistakenly said to be the perpetrator when in fact they weren't. It was a false alarm. That is versus the 10% false alarms from the sequential method. So the question then is, well, which method is best then, right? And really that is kind of up to society, right? That is up to your values, right? If you are somebody who's like, no, everybody should be incarcerated, then maybe the sequential method is what you or your government or your criminal justice system is looking for, and that maybe it doesn't matter if false alarms are not important to you. I think we would agree in America that false alarms and false accusations, we want to reduce those as much as possible. And so maybe the simultaneous method is the most important method. So yeah, maybe that means that sometimes people go free who were guilty, but the cost of that is that we're reducing the false alarms in which we do. But if your goal is to, by any means necessary, try to get the perpetrator, then maybe you should go with the sequential method. But if you do, you're going to have a lot of people that are falsely accused in that lineup style method. And that's why it's important to look at signal detection theory. The D prime here, the sensitivity, would tell us then that our sensitivity is highest for the simultaneous method than it is for the sequential method. All right. Now, if you want to take a quick break, we're entering into the final stretch here. This will probably be about 10-15 minutes before we are out of here. All right, so I'm hoping that what we're going to be talking about here is probably review for a lot of you. If not, the book goes into more detail, and there's so many resources online and videos for brushing up on your neuroscience and your neuropsychology. But I wanted to kind of review over some of the big ideas because we're going to return to these again and again this semester. The first is the layout of the brain. So the layout of the brain is like this, where we have the frontal lobe up here. We got the parietal lobe, we're a little bit behind that. In the very, very back, we have the occipital lobe, and then underneath it all, we have the temporal lobe. I remember this from a very handy mnemonic called FPOT. So don't let your brain go to waste. FPOT. And if you remember FPOT, then you can get it. It's a joke about marijuana. Frontal lobe, the F is frontal. It comes first. Then if we're moving clockwise, we have parietal for P, occipital for T, for O, and temporal for T. That moves clockwise like that. What do each of these areas do? Frontal lobe is going to be used for a lot of executive behavior, so looking at reasoning and logic and creativity and planning and attentional control and things like that. That's going to be your frontal lobe. Beyond that, we got our parietal lobe back here. This is going to help us kind of understand and process space and touch and geography, even math can kind of end up in here too. The occipital lobe is going to be used for seeing, almost exclusively is for seeing. Some of that is going to be for maybe recognizing visual components, but a lot of it's going to be for vision. And then the temporal lobe is going to have a lot of hearing and also a lot of recognition components too. So when we start talking about speech, when we start talking about hearing, we're going to be talking a lot about the temporal lobe. When we talk about vision, we're going to be talking about a lot about seeing in the occipital lobe. When we talk about touch, it's going to be the parietal lobe. And when we talk about smelling and when we talk about taste, we're going to be talking about some frontal lobe stuff, but really kind of a combination of some of these areas. The textbook is going to throw this at you. Don't worry too much about the different nerves. We're going to be learning about these individually. You will not need to label any kind of map like this to look at the different nerves, but they are important. We'll be talking about the optic nerve, the olfactory nerve, the vestibular ocular nerve, and I think that might be the ocular motor nerve. But those are kind of some of the vestibular nerve and the auditory nerve. We're going to be talking about those two. But the point is that from our brain, we have a lot of nerves that are going to interact with other areas of our face and of our body that help us move and react to what we are experiencing. This next piece is something that you could spend an entire semester covering. And if you take Dr. Manella's biological psychology class, you will spend an entire semester talking about neurons. But neurons are the building block of our nervous system. And so in order to understand perceptual processes, it's important to understand how neurons work. Neurons are, as I said, the building block of the nervous system. And I think we got about 70 billion neurons. That estimate changes sometimes. Some people will say it's up to 100 billion, but it kind of fluctuates depending on who you're asking. And these neurons are going to be responsible for different things. Some neurons are going to be responsible for vision. Some of them are going to be responsible for hearing. Some of them are going to be responsible for detecting coldness and warmth and pain and so on and so on and so on. The important thing here is that neurons do not carry a stimulus's strength. So when we talk about a neuron and conveying a signal that is strong, that neuron is not firing really hard, nor is it going to fire really soft. A neuron is like a toilet. It either flushes or it doesn't flush. Once you pull that plunger, once you push it down, it flushes, and that's that. Neurons are like that. The neuron is going to fire or it's not going to fire. The real difference here is that neurons are going to fire more, fire less, or fire the same rate. I'm going to say that one more time. That neurons are either going to fire more, they're either going to fire less, or they're going to fire the same. And the reason why I think that's important is because when we talk about the brain is a super complex organ, but it only really understands 3 words: more, less, or the same. When it comes to neurons, it can detect if neurons are firing more, it can detect if neurons are firing less, and it can detect if neurons are firing the same as they were. And that's what our brain uses to interpret what we are experiencing in the world around us. This is a very rudimentary, and we'll come back to this idea over and over and over again this semester. I love to say that action potentials, those electrical impulse, that's what an action potential is. An action potential is the electrical impulse that a neuron fires. That an action potential, that's the language of the brain, and that language only has 3 words: more, less, and same. Here is a rudimentary neuron, and these neurons have dendrites. These are these are like the branches that detect incoming neurotransmitters, the chemical signals that are passed between neurons. Those dendrites are going to communicate with the cell body how much neurotransmitters they get. Once they get enough, that cell body is going to signal a change. We call that change depolarization, and it causes an action potential. Basically, we have a lot of sodium, which is negatively charged, is going to float into to that cell body, and as a result, it's going to fire an electrical impulse down the length of this axon. Shortly after that happens, then potassium ions are going to rush in there to return that cell back to its happy medium resting potential, which I think is like -70 or something like that. While that's happening, that electrical impulse is firing down the length of that axon. And once it does, it's going to stimulate these terminal buttons. Sometimes you'll hear them called synaptic terminals, terminal buttons, axon terminals. They're named a lot of things. I call them the terminal buttons because I'm a little bit old school. But if you want to call them axon terminals, that's okay too. But they are these little buttons down here at the end that also have a lot of neurotransmitters in them. And whenever they are stimulated, they are going to send out neurotransmitters onto the next neuron. This happens in the blink of an eye. Even faster than that. It happens in the span of milliseconds. This happens extremely fast. This is just one neuron communicating with the next, and this happens across the brain all the time, everywhere. We got 70 billion neurons that are doing this day in and day out, and it feels automatic. It feels immediate. Here is what this looks like at the end of a terminal button. At the end of an axon terminal, and so we can see how these little neurotransmitters are floating across the synapse, across this this gap between neurons, till they get to the next dendrite here, where they will go get processed again. All right, I don't want to talk about this too much because I already talked about it. This is just the axon and how the action potential moves across the length of that axon. Here they have that at a fraction of a second, a 1/10 of a second, roughly. How do we know this? Because how do we know what areas of the brain do what? We know this because of lesion studies. Lesion studies are whenever we experience some kind of trauma to our brain, and that changes how the brain works. And so we can look at across history cases of this, like probably the most common or most famous of this is Phineas Gage. If you remember hearing about Phineas Gage, he was a guy that had a railroad spike driven up through his frontal lobe, and people noticed that his behavior changed afterwards, and they attributed that change in behavior to his frontal lobe. There's a lot of historical debate about the degrees to which we can generalize those findings and how much they explain his behavior, but that is a conversation for another day. The point is that if you damage someone's occipital lobe, they won't be able to see. End of story. If you were to take out somebody's occipital lobe, they can't see. That's how we know the occipital lobe is responsible for vision. If you damage someone's temporal lobe and they stop speaking, then you know that that area of the temporal lobe is responsible for their speech. So people use lesion studies in order to understand what areas of the brain do what. Generally speaking, this stuff, because it's permanent, is not ethical to do on somebody, right? And so we have developed a device that can temporarily disrupt brain activation, and that's called transcranial magnetic stimulation, or TMS. It delivers a very fast, very powerful, and direct magnetic pulse, and that is going to temporarily disrupt activation in that part of the brain. And so that's how we can determine if you're zapping that part of your brain that is responsible for speech and you're unable to speak, then that's how we know this area is for speaking, and this area is for listening, and this area is for singing, and this area is for detecting things on your shoulder. This area is for moving your hand, and so on and so forth. We can use this device to do that. I put a link at the very, very beginning of these lecture slides in case you wanted to see one of those in action. It's really, really cool. People actually use this these days, not just for research, but also for application. People use this as a way to treat medication-resistant depression, actually, in areas of clinical work. So basically, they strap you in, they keep your head still, and they deliver this really strong magnetic pulse to a cluster of neurons that disrupts it for a moment. And then whenever it turns off, everything's back to normal. There's also, so that's lesion studies. The other way that we are able to understand what areas of the brain do what is through neuroimaging. And neuroimaging is whenever we measure some kind of brain activation, and then based on that activation, we draw inferences about what area of the brain is responsible for what kinds of behaviors. And in a previous life, I used to do neuroimaging work. My background is in MRI, in fMRI, I should be more specific. But honestly, and even though I feel like people think of the classes that I teach as like the brain classes, always be careful whenever you're interpreting neuroimaging results, because people love to show you images of brains, or they love to kind of like say like, yeah, in an MRI study, they found this. And it's very, very easy to mislead people about those things for reasons that I'll explain in just a moment. So if you're listening to a podcast and you got some kind of scientist who's like, oh, you definitely got to shower, you got to do a cold shower in the morning because it's going to raise your dopamine levels, you got to be careful about the interpretation of what that actually does, because a lot of times the way that we understand that increase comes from a very indirect measurement, which you'll see in just a moment. So when we talk about MRI or PET or EEG, those are actually indirect measurements. So the rationale generally for these techniques is that if we can figure out where the blood is in the brain, then we can understand what parts of the brain are active. It makes sense, right? If you were to work out with a dumbbell just on your right arm is going to get a lot of blood flow because it needs blood flow to stay active and stay oxygenated. Same idea for the brain. So essentially, when we are doing things like PET or MRI, what we're looking at is where in the brain is the blood. And based on that, we're able to say, like, okay, that's how we know that whenever somebody is speaking, it's that this area is involved, because when they were speaking, that area of the brain recruited a lot of blood to keep going. There are individual strengths and weaknesses for this, and we're going to, throughout the semester, we're going to look at a couple of different measurements, and so it's good to know, like, all right, they use EEG, they use single cell recording, which means that this is one of the things they can study with it, and this is one of the things they can't study with it. So EEG, electroencephalography, this is measuring actual electrical activation on the surface of the brain. So this is as direct as you get with neuroimaging, pretty much. Well, single cell recording is probably more direct, but EEG is measuring the action potentials that are generated across the surface of the brain. This is whenever you see people with these kind of funny little skull caps on. What they're measuring here is they're measuring for electrical activation across your brain. It's very fast. It's relatively cheap. If Westfield got any of these neuroimaging devices, it would almost surely be EEG because it's affordable in that way. The weaknesses, though, are that the data is very, very noisy. So, for example, if you're looking at this trend right here, what the heck does that actually mean, right? That's hard to kind of interpret. And this is, each one of these little electrodes is going to have its own really complex, I thought I had a figure to kind of show you, but I'll show you later. It can get really, really messy, and interpreting it can be really, really hard to do. And it's also really hard to measure the deep areas of the brain. And the reason for that is because when we're trying to measure the deep areas of the brain, we're also gathering all the electrical activation from the top too. So it's really hard to kind of get those deep brain areas. Those are some of the weaknesses here. MRI is looking at indirect measurement of blood flow, and I should specify here that I'm really going to be talking about fMRI. Well, hold on. Actually, when we're talking about structural stuff, so this figure right here, this is an MRI. This over here, which has activation, is an fMRI. The F just means functional. Sorry, y'all, I had to pause it because I heard a little scratching at the door, and I thought it was my dog, but it was actually my spouse who was asking, is pizza okay for dinner? Which, of course it is. Of course. You don't even have to ask that. All right, so when we're talking about activation, we're talking about fMRI. fMRI is for functional MRI. And it's funny that my spouse came over because she's actually a neuroimager. She actually does PET imaging, which we'll talk about in just a minute. She does that at Yale University because Westfield cannot afford a PET device. But we'll talk about how expensive PET is in just a minute. To conclude my thoughts here about MRI, though, MRI, if you're just talking about structure, you're talking about MRI. If you're talking about activation or what areas of the brain do what, we're talking about fMRI in that case. Now, the thing about fMRI is that what it measures is indirect blood flow. It actually measures, I believe, hydrogen ions that are carried in blood, in oxygenated blood specifically. And so keep that in mind whenever you're looking at this this activation right here. If somebody was to say, like, yeah, this is the area that was active whenever somebody was looking at a picture of coffee, then what that means is that in these areas, there was an increase in hydrogen ions that could be measured using a really intense magnet. And we take that to believe that meant that there was a lot of blood there, and what we then can infer, if there was a lot of blood there, that must mean that that area was active and was doing a lot of work and recruiting a lot of blood. You can see that's a couple of kind of assumptions you have to make there, right? So that's why I was saying that, like, when it comes to neuroimaging, be careful, take it with a grain of salt, because people love to overgeneralize and really kind of dive into conclusions and not be skeptical about this stuff. I love neuroimaging, but I also love skepticism too. The strengths of MRI is that it's relatively affordable. Once you buy an MRI scanner, that's the hard part. That's the expensive part. The maintenance of it is not as bad. It is high resolution. In other words, you can see really, really well. It gives you good data that's easy to interpret usually. The weaknesses, though, is that it does require a lot of inferences. We just walked through some of those. It is relatively slow, so if you look at coffee, it takes roughly 6 seconds for your brain to recruit extra blood for that to occur. So you have to take that to account whenever you are drawing conclusions here, and it also requires that subjects lie absolutely still. They're not allowed to move whatsoever. PET imaging is positron emission tomography, and this is where you attach a radioactive tracer. You inject it into someone's arteries. That goes into their blood system. That specific radioactive tracer is meant to bind onto usually a specific neurotransmitter, where maybe you're going to have a radioactive tracer for dopamine. And so you inject somebody with that, and then you scan their brain to look to see where those radioactive isotopes have gathered. That is how PET works. Yes, you heard that right. There's a lot of radioactive stuff going on there. This is why it is one of the weaknesses, obviously, is that it's radioactive, and you can't really do more than 1 or 2 of these studies a year for that reason. It's extremely expensive. I want to say that most participants, in order for the researcher to collect that data, it costs the researcher about $7,500 up to $10,000. So it can be a lot of money just to run these. So think about that, right? Like whenever we are looking at a study, if it's a PET study and they only have 20 people in it, it's very easy for us to turn our nose up and say, this is a really small sample size, don't you think? But think about if 20 of those people cost $7,500 each. I ain't got that kind of money, right? So that's one of the weaknesses here. But the nice thing about it is it does tell you exactly where that blood is. And that can tell us exactly where dopamine is or where serotonin is throughout the brain, which is extremely valuable. All right, and that is all that I have for you here. I'm sorry that this went on so long, but I warned you that it would be about 80 minutes or so. Thank you so much for tuning in. Chapter 2 is not going to be nearly as long because we're going to be talking about the anatomy of vision. So it's a chapter that's almost exclusively about anatomy, so it's kind of a shifting gears. Excuse me, I had a burp there. It was a yawn and a burp. I don't know how to explain that. Was that sensation or was that perception? I don't know. Anyways, if you have any questions, feel free to let me know. Feel free to send me an email. I would be happy to talk with you more about this stuff. Thanks so much for tuning in, and I will see you later. Bye.